Episode 2, Markov Decision Processes. Last episode, we built intuition. We watched an agent stumble through a grid world, learn from rewards, and gradually discover a strategy. It was powerful, but it was informal. Intuition alone can't solve hard problems. We need a precise language. Today, we're going to take every concept from Episode 1, the agent, the environment, the states, the actions, the rewards, and express them in the language of mathematics. By the end of this episode, you'll be able to look at any RL problem and describe it with a single, elegant mathematical object, the Markov Decision Process. Let's recall the core of Episode 1. An agent observes a state. It picks an action. The environment responds with a new state and a reward. Then the loop repeats. We used words like state, action, and reward, but we didn't define them precisely. What exactly is a state space? How do we describe what happens when the agent takes an action? How do we capture the idea that rewards now are worth more than rewards later? The MDP gives us answers to all of these questions. It wraps the entire agent environment loop into 5 precise components. Let's build it piece by piece. A Markov decision process is defined by a tuple of 5 elements: S, A, P, R, and gamma. S is the state space, the set of all possible situations the agent can be in. A is the action space, everything the agent can do. P is the transition function. It tells us the probability of reaching each next state, given the current state and action. R is the reward function, the number the environment hands back after each transition. And gamma is the discount factor, a number between 0 and 1 that controls how much the agent cares about future rewards versus immediate ones. 5 components. That's it. Every RL problem we'll study in this course, from grid worlds to go to robotic control, can be written as these 5 elements. The MDP is the universal blueprint. The transition function P is where dynamics live. Given that the agent is in state S and takes action A, P tells us the probability of landing in each possible next state S prime. In our grid world from Episode 1, transitions were deterministic. Move right, and you always end up 1 cell to the right. But many real-world environments are stochastic. Imagine a frozen lake. You try to move right, but there's a chance you slip. Maybe 70% of the time, you go where you intended. 20%, you slide forward. 10%, you slide backward. The transition function captures this uncertainty precisely. For every state-action pair, the probabilities over all possible next states must sum to 1. This is a fundamental constraint. The agent must end up somewhere. Deterministic environments are just a special case, where one next state gets probability 1 and everything else gets 0. The reward function R assigns a number to each transition. The agent moves from state S to state S prime by taking action A, and the environment returns R of S, A, S prime. In our grid world, reaching the goal gave +10, falling into the trap gave -5, and every ordinary step cost -1. That living penalty that nudged the agent to find the goal quickly. Notice that the reward depends on 3 things: where you are, what you did, and where you ended up. This is the most general form. Some problems simplify it. Reward depends only on the state, or only on the state and action. But the full form handles everything. Gamma, the discount factor, answers a deceptively simple question. How much does the agent care about the future? A reward received right now has full value, but a reward 1 step in the future is worth gamma times as much. 2 steps away, gamma squared. 3 steps, gamma cubed. Each step into the future multiplies by gamma again, so distant rewards shrink geometrically. When gamma equals 0, the agent is completely myopic. It only cares about the very next reward. When gamma equals 0.99, the agent is far-sighted. It values rewards 100 steps away, almost as much as immediate ones. Look at the difference. With gamma of 0.5, rewards decay quickly. By 10 steps out, they're worth less than 0.1%. With gamma of 0.9, the decay is gentler. Rewards at step 20 still matter. And with gamma of 0.99, the agent looks far into the future. Rewards 50 steps away retain 60% of their value. Most practical problems use a gamma between 0.9 and 0.99. Too low, and the agent makes short-sighted decisions. Too high, and learning becomes slow and unstable. Now we can define what the agent is actually trying to maximize. The return, written G sub t, is the total discounted reward from time step t onward. G sub t equals r at t plus 1 plus gamma times r at t plus 2 plus gamma squared times r at t plus 3, and so on. Each future reward is discounted by an increasing power of gamma. There's a beautiful recursive structure here. The return at time t equals the immediate reward, plus gamma times the return at time t plus 1. This recursive form will become the foundation of the Bellman equation in the next episode. The return captures a complete trajectory's worth of value in a single number. When the agent learns a policy, it's learning to maximize the expected return from every state. A policy, written as pi, is the agent's strategy. It's a mapping from states to actions, or more precisely, from states to probability distributions over actions. When pi of a given S assigns all probability to a single action, we call it a deterministic policy. The agent always does the same thing in that state. But policies can also be stochastic. Pi of a given S might say, go right with 60% probability, go up with 30%, and go down with 10%. The agent rolls the dice each time. Why would you ever want randomness in your strategy? Remember the exploration-exploitation dilemma from episode 1. A stochastic policy naturally explores. It doesn't always pick the same action, so it discovers new possibilities. The ultimate goal is to find pi star, the optimal policy. That's the policy that maximizes the expected return from every state. It's the best possible strategy, and every algorithm we study in this course is searching for it. There's one more concept that makes MDPs tick: the Markov property. The future depends only on the present state, not on how we got here. This means the current state contains all the information the agent needs to make optimal decisions. The full history of past states, past actions, past rewards, none of it matters beyond what's captured in the current state. The state is a sufficient statistic for the future. Let's make all of this concrete. Remember our 5x5 grid world from episode 1. Let's formalize it as a complete MDP. The state space S has 25 states, one for each cell. We can label them as row-column pairs, 0, 0 in the top left, 4, 4 in the bottom right. The action space A has 4 actions, up, down, left, and right. The transition function P is mostly deterministic. Take action right in state 1, 0, you move to 1, 1 with probability 1. But try to move into a wall, you stay put with probability 1. The reward function R, reaching the goal at 4, 4 gives plus 10. The trap at 2, 3 gives minus 5. Every other transition gives minus 1. And gamma, let's set it to 0.95. The agent cares about the future, but not infinitely so. 5 elements. That's the complete mathematical description of our grid world. Every behavior the agent learned in episode 1, the stumbling, the exploring, the converging on a policy, all of it happened within this formal structure. We just didn't have the language for it yet. And this is the real power of the MDP. It's not just a way to describe grid worlds. It's a universal language for sequential decision-making. A self-driving car navigating traffic. The state is sensor readings. The actions are steering and acceleration. The transitions depend on traffic physics, and the reward reflects safety and progress. That's an MDP. A recommendation algorithm, choosing what video to show next. The state is the user's history. The actions are the available videos. The transitions capture how the user's preferences evolve. And the reward is engagement. That's an MDP too. Once you see the pattern, you see it everywhere. Every problem with states, actions, and rewards, from games to robotics to finance to healthcare, fits into this one framework. The MDP doesn't care about the domain. It only cares about the structure. Let's lock in what we've built. First, the MDP is defined by 5 elements: states, actions, transition probabilities, rewards, and the discount factor. These 5 components describe any sequential decision problem. Second, the return is the total discounted reward from any point forward. Maximizing the expected return is the agent's objective. Third, a policy maps states to actions. The optimal policy pi star achieves the highest possible expected return from every state. In the next episode, we'll ask a deeper question: how much is a state worth? We'll define value functions, V of S and Q of SA, and derive the Bellman equation, the recursive relationship that makes RL algorithms possible. See you there.